Thank you. So if everything's okay, you should hear, see me, and see my slides.
Yes.
Sorry, I cannot do it in German. My German is about as good as a goalkeeper, Belgian goalkeeper that once played in Bayern München, Jean-Marie Pfaff, which is to say, not very good. My German. So, okay, let's dive right into it. We see that some trends are happening in automotive that are actually leading to significant changes, right? There is increased electrification of vehicles, either hybrid vehicles or fully electric vehicles. There's a rise of software-defined cars, making operations, adding functionality, enabling features, all through software increasingly. And there's also an evolution towards autonomous driving, also known as driverless cars, which actually combine lots of sensors and software to control and navigate the car. Now, these trends, of course, increasingly strain the current in-vehicle communication networks and increases the requirements on what they need to do. The first one, in terms of electrification, for example, with an increased electromagnetic interference or EMI risk, requires increasing immunity for the communication network from that electromagnetic interference. The second one is about maximizing the range, for example, in electric vehicles to minimize the vehicle weight. And the wiring harness, being consisting of copper cabling, metal cabling, can gain some quite significant weight that could be minimized, or that should be minimized. And then lastly but not least, the increasing reliance on the software and on sensors actually leads to increasing data rate requirements. For example, think of having to transmit uncompressed sensor images or camera images with a minimal latency, so avoiding the encoding and decoding, gives rise to quite significant data rates that then might be processed centrally in the AI inference step, for example, to operate on that data. So these trends actually resonate very well with optical fiber characteristics, and that's also why the automotive Ethernet standard has been brought to life in an optical version as well, optical automotive Ethernet. And so fiber technology in general is not susceptible to electromagnetic interference, easily achieves these high data rates, and has a significant weight advantage versus copper. It's also a mature technology currently being used to provide broadband connectivity. So there's a large body of work and a whole industry behind this proven technology. And this presentation here is about exploring whether there's anything we can leverage from one sector into another. One of the benefits our fiber broadband connectivity could bring to automotive sector. Is it viable for inclusion in future vehicles, for example? So why am I talking about that? I'm actually a technology advisor at Nokia. I'm actually scouting for trends and opportunities. My previous role was actually department head of fixed networks research at Bell Labs, including research on optics. And I actually became aware of Arena 2036 of it being an interesting place to explore new concepts. So here we are. So the outline of what I want to go through today is firstly give a short overview of fiber broadband deployments and use for primarily broadband connectivity today. Second, go into a bit of the technical characteristics of this fiber to the home communication technology with an emphasis on what's a bit special about this technology and different than other alternatives out there, for example, optical automotive Ethernet. And then finally, try to explore whether this matches the automotive specifications and address the need or opportunity for tailoring it to the use case. So today, actually, fiber networks are quite a mature solution for broadband connectivity. And this one plot gives a worldwide overview in terms of what technologies people are connected to use the internet. And notice this number of households, so it's smaller than number of users. Typically, there's more than one user behind a single household. But as you can see, these numbers are quite impressive for fiber. So there's at the bottom, you see the number of fiber connections. Above that, you see DSL connections using the telephone wiring. Above that, you see cable connections using DOCSIS technology, for example, offered by Vodafone Deutschland. And then on top of that, you see fixed wireless access. And it is kind of a technology using a fixed antenna on the house to actually over 5G technology receive a data connection. And on top, you have other, for example, like satellite connections. So worldwide, you can see that actually fiber today has most subscribers. It's a very, very mature technology. A big majority of them are in China, but over 100 million are actually in Europe. And by 2025, actually, we will have more than 1 billion fiber subscriptions or households connected to fiber worldwide. And as a technology, it's also increasingly adopted for enterprise networks under the umbrella of what's called Passive Optical LAN. So it actually replaces a traditional enterprise network, which I illustrate here, which consists of Ethernet LAN networking with Ethernet cables, twisted pair cables, which have 4 twisted pairs in there, and lots of active switches to patch together all that cabling. Now, the passive optical LAN solution is actually replacing those Ethernet cables by optical fiber cables, and also replacing all the active equipment, the aggregation switches, by passive optical splitters. And actually, the benefits it brings is it has a much lower power consumption overall. There is less hardware to deploy, so the use of less floor space. There is no requirement of replacing any of the Ethernet cables when you upgrade to a different Ethernet technology, which is needed today. And it's also more reliable and more secure. So with that, you've seen that fiber to the home is quite an established industry, is mature, and is already growing a bit into enterprise sector. So now we'll go into introducing fiber to the home and look into some of the technical characteristics. A big majority of fiber broadband out there uses this passive optical network I've mentioned before, and I will focus on that specific type here. There is a small segment that uses point-to-point Ethernet, optical Ethernet, but it's actually negligible within the fiber broadband deployments. And so within that passive optical network type of fiber technology, there are many different generations, and they have steadily increased the data rates. One of the older generations is what we call GPON. The PON there stands for passive optical network. It's gigabit PON, able to achieve data rates up to 2 gigabits per second. And that is actually already massively deployed throughout the world. And now currently, the ongoing massive deployment is XGS-PON, which is a 10 gig symmetrical passive optical network technology. And now there have been already deployments started on a technology called 25 gig PON, of course, enabling 25 gigabit data rates, and we are already trialing 50 gigabit per second PON as well. So you can see that actually fiber broadband technology as a technology kind of effortlessly supports already very high data rates, up to 50 gigabits per second. And cost is always an important design target for PON. And so all the generations, for example, use a very simple modulation mechanism. It's called on-off keying, basically meaning if the light is on, it's a bit 1. If the light is off, it's a bit 0. And it's used by all technology generations so far, including 50 gig PON. It's also using bidirectional communication over a single fiber, meaning it only requires a single fiber to work, not a fiber pair. And so the communication is bidirectional and simultaneous. It's really full duplex on a single fiber, using a different optical wavelength for upstream and downstream direction. And so also when you connect these end devices, you only need to connect a single fiber and not 2 of them. Then in terms of architecture, it's called passive optical network, and the passive stands for the fact that there's actually no amplification in the field whatsoever, allowing for a minimal operational cost. And so it's also a shared network, therefore, that has optical power splitters with typical split ratios of 1:32, 1:64, for example. And actually, it's this splitting of the optical power to different endpoints that is actually the dominant loss contributor. It's actually much larger than the fiber loss, which is relatively low. And the reach you can get with current technologies is 20 kilometers and even more. So a typical reach is 20 kilometers. In downstream direction, the transmission in downstream is actually quite continuous. So it's broadcasted to all of the households in a time division multiplexing scheme. So each one gets a specific time slot, and all the endpoints only decode the parts that are meant for them. And it uses relatively small frame sizes of about 125 microseconds, but these can be even smaller as well. In upstream, it's not using continuous transmission, it's actually using burst transmissions. So all the modems get a specific time slot for transmitting their data upstream. So it's time division multiple access, or TDMA, And of course, these modems therefore need to be ranged. You need to measure the propagation delay so that you properly align all of the incoming bursts one after the other at the single optical receiver. And so this is quite an illustration of actually two different architectures, so point-to-point architecture and the point-to-multipoint architecture, so the point-to-point at the top. One thing that you can readily notice is if you compare these two types of architecture is that the top one, the point-to-point one, has more transceivers. On the central part, it has as many transceivers as it has links. And so in an environment that might require redundancy, for example, by having redundant hardware, redundant transceivers, you actually end up with 4N transceivers if you have N links. In terms of switching requirements, and you also need to connect all these different things together or switch the data to a central processing location, the input-output rate of the switch is actually simply N times the link rate. It needs to be a full duplex, and therefore also your switch capacity can be up to twice the link rate times the number of links that you have. So if you don't have a proprietary switch design, you often need to make some trade-offs on the switch between port counts, the number of inputs, as well as the forwarding capacity that it has, which often results in an over-dimensioned forwarding capacity of the switching. Compared to point-to-multipoint architecture, they can readily notice that you have, of course, less transceivers centrally. You have a single one. And so to obtain fully redundant optical hardware, you only need 2N+2 transceivers, for example. The actual topology is a point-to-multipoint, but it can be whatever. It can be a star topology. It could be a 3M branch topology. There's no specification. There's just one receiver and multiple transmitters. In terms of switching, because of that architecture, you already have kind of an ideal Ethernet switch happening within the network. So in terms of input-output rate towards that switch, you would only have 1 times the PON rate. And you also have potential statistical multiplexing benefits, especially if the data rates on the network are very different in terms of peak rate versus average usage rate. And finally, of course, because of its architecture, it's also easily or readily expandable. You can simply add another endpoint to the network by connecting an additional fiber to the splitter. So it could be, and I'm speculating here, useful for adding new features to the car or reuse over different models. Okay, so now that we know how PON works on a high level, with this final part, I'd like to go into how it could match automotive specifications, addressing the need and opportunity for tailoring it, and also addressing overlap with other work ongoing already in the telco industry. So some examples for potential tailoring of PON technology is, of course, I mentioned, it is capable of transmitting with to distances up to 20 kilometers, which is, of course, quite an overkill if you're talking about an in-vehicle network inside a car. So reducing the 20 kilometers to, for example, a 40-meter range, which is actually the optical automotive Ethernet spec, would, of course, require to use cheaper optics, for example, by using a different optical wavelength, and also cheaper fiber. And the fiber used in fiber to the home deployments is typically single-mode fiber, while for these shorter ranges, you could actually use cheaper fiber like plastic fiber and, for example, not single-mode fiber, but multi-mode fiber. The second dimension of simplification is, of course, number of endpoints. The PON technology for fiber broadband has been designed to support up to 256 endpoints on a single optical upstream receiver, which is quite a lot. In a car, I'm not sure how many endpoints there would be for this particular use case, but if you decrease it to 4 or even 16, this still enables quite a lot of simplification and also speed up of what's called the medium access control. And this is kind of the scheduler, the master of the transmissions on this shared medium, the MAC layer. And then, of course, there is a question on determinism. Because it's a shared technology, you might wonder, would such a technology be able to operate under strict timing requirements? Well, there's actually quite a lot of use cases already being tackled in PON technology with on that. And one of them I'd like to mention here is, for example, mobile front haul, where you have different 5G small cells, but the scheduler is actually not located within the small cells. The scheduler for the 5G is actually located here on the left, right? This is where the 5G scheduler is. So you have two things here. You have the PON scheduler. This one is in charge of the transmissions on the optical fiber. So he tells every PON modem, you can now transmit, and make sure they don't collide. On the 5G front, you have the 5G scheduler, which actually tells the smartphone on the other side of the small cell, when he can transmit, on what frequency slot, on what time slot. And so actually the trick that we're applying to actually make this timing sufficiently synchronized, because there's a limit on the timing difference between when the scheduler sends it out and when his upstream transmission needs to be received. Well, we do that by having the schedulers of 5G and PON actually collaborate. So basically, the 5G scheduler gives a head up to the PON scheduler, hey, there's a transmission arriving in 2 milliseconds of a smartphone that you might actually want to proactively allocate a slot for, so that when it arrives in the wireless interface, it immediately has a slot to be forwarded on the PON link. And so that way you can actually achieve quite deterministic and very tightly synchronized timings on the overall end-to-end link. And a proof point that's actually ongoing in other work that Bell Labs is doing with Arena 2036 is on using PON for industrial applications. And so there we've demonstrated that it actually interoperates quite nicely with IEEE time-sensitive networking, so TSN. And so that demonstration was actually about having TSN flows running transparently over PON equipment. And so for those familiar with time-sensitive networking, you'll know that that actually operates in a way to open all of the gates for the packet going through synchronously throughout the entire link. So the packet can go through without any additional delay. Well, here we've used the same mechanism. So we've had the TSN scheduler talk to the PON scheduler. And we're actually demonstrating here kind of co-scheduling of PON and TSN switches and combine TSN traffic with best effort traffic on the same system. And so the results of that optimization actually show that PON can transmit deterministic TSN traffic without any issue. And you can see here, for example, for the best effort flow, you get a more significant, though still very low jitter of hundreds of microseconds. And actually, we've managed to decrease the latency and especially the jitter, which is the latency variation on TSN flows, to only 0.5 microseconds for TSN flow 1 and 0.2 microseconds for TSN flow 2. The difference being that this one includes some extra TSN switches still in the path. So to go back to the start of my talk, there have been these trends recently: software-defined car, autonomous driving, electrification, that have been putting increasingly demanding network requirements on the in-vehicle network. For example, on electromagnetic interference, on the data rates, on the weight of the entire network. And actually, they match pretty well with optical fiber. And fiber being a very mature solution for broadband connectivity, and nearing 1 billion users today, there is already a large body of work out there in the telecom industry. And here, the open question is whether there's anything we can leverage from that body of work to in-vehicle networks for automotive. And I especially want to call out anyone who might want to explore that path to reach out to us to answer that question.